Organometallics. We'll pick up where we left off and finish up a few notes on type alkene additions, and then that will provide a natural segue into the main topic of today's lecture, which will be allylic substitution reactions. As you'll remember, last time we discussed Walker type alkene additions to pi systems with our specific focus on olefins. And I won't say too much more about that in the interest of time, but I would like to emphasize that in addition to olefins, other CC pi systems can engage in both Heck and Walker type alkene additions, and these generate differentiated intermediates with their own with their own properties and synthetic utility. So if we consider extending the framework we discussed last time to alkynes, then you'll notice that we'll just consider the case of terminal alkyne here. You'll notice now that the intermediate that is thusly generated is an alkenyl metal, or specifically an alkenyl palladium species. Several potential regio and stereochemical outcomes that are possible here. I've drawn just the two potential stereochemical outcomes, depending on the operative mechanism, inner sphere or outer sphere nucleopalladation. And this can be a powerful way to synthesize substituted alkenes because these alkenyl palladium species can react further with various electrophiles. Analogously, and this will be the tie-in to today's lecture, we can carry out alkene additions to 1,3-dienes or 1,2-dienes, aka allenes. And in these cases, the intermediates or the products that are thus generated are allyl metal species. Here too, let's first consider the case of 1,3-dienes, two flavors possible, inner sphere nucleophilic attack or outer sphere nucleophilic attack that establishes the relative stereochemistry of the palladium and the nucleophile. And then the downstream reactivity of these species, just think allylic substitution chemistry. We'll see examples of that shortly. Allenes offer an interesting hybrid sort of reactivity between the two modes I just introduced, depending on which regiochemical orientation the nucleophile adds into the pi system. So if the nucleophile adds to the allene terminus, then you would generate an alkenyl palladium species, and then that would react analogous to the alkynyl case. The most common situation, however, is that the nucleophile will add to the internal case. And then you would generate an allyl palladium species. And again, then we'll elaborate on the reactivity to expect from those types of species. So that's just a quick means of orienting you in terms of other types of possibilities that are out there in terms of addition to the pi systems. So let's talk about Heck type carbopalladation here. And I realize some of this might be reviewed to, this may be reviewed to some of you, but we'll zoom in with quite a bit of detail here just so that everyone's on the same page. And then moving forward, we'll discuss this with a little bit less detail. So let's first consider how mechanistically how this is working. So the difference between what we saw before is now we have our migrating group, the aryl species, directly attached to the metal. It can coordinate to the alkene, and then the transition state here. Wenji, walk us through what's going to happen here. Transition state, and then the product.
In the transition state, you would have we weakening of the arrow palladium bond.
Okay.
Also double bond. So it's like a 4-member ring.
Okay. Position state. For trading, pi bond here for sigma bonds. Oops, and I need the partial. I guess I can move this reaction. I'll draw now the implicit H atoms here just for completeness sake. Okay, and then now what's going to happen next? So let's form those bonds first fully.
General natural. Adding to side.
Okay.
So fashion.
All right. And what's next?
In a head type validation, you would then evoke the beta hydride.
Okay. What has to happen to set up the beta hydride elimination?
First need to rotate the single bonds.
Okay. Beautiful. This is a key feature to consider. This is really the reason why I wanted to draw this out in detail. So now you need to rotate to get your beta hydrogen syn, and then the last step, I think Wenji said, is going to be beta hydride elimination. Now, what happened overall to the relative orientation of the two R groups? So they're now in a trans relationship with respect to each other, whereas in the starting material, they were in this relationship. Byproduct here, palladium hydride, we'll draw that bound here. In presence of base, this will be quenched to give a palladium 0 species. Okay, very good. So one of the signature features of a Heck type reaction is this inversion of the alkene stereochemistry. That's important to be aware of. Okay, let's look now at some early history here, just in parallel to our discussion of the Wacker type, development of the Wacker process and related reactions. So let's consider some of the early reactions here that were performed. We'll consider first one by Fujiwara, and Fujiwara reacts this complex palladium styrene dichloride in the presence of an arene and acetic acid as solvent. So first, let's define more rigorously this starting complex, palladium dichloride styrene. I have this drawn in quotes, meaning that this is not the actual, this is the molecular formula, but not the actual coordination structure. So what would be the coordination structure here, Shenghong? Do you expect palladium to be 3-coordinate?
No, probably bridging chloride.
Bridging chloride, okay, very good. Now here we go. We're going to treat this bridging chloride dimer with acetic acid. In acetic acid, this dimer will get broken up in all likelihood. The product here is the trans still being shown. And the intermediate that's generated, we have arene, we have palladium 2, and we have acetic acid. So can someone from Jin's group, Annabelle, what is this a recipe for?
First, breaking the carbon hydrogen bond of the array.
Beautiful. Arene CH activation by could be by a concerted metallation deprotonation mechanism, could be more of a Friedel-Crafts type addition, but this combination of carboxylate type base, or in this case, it's protonated, but carboxylic acid, plus arene CH bond, plus palladium-2 as a recipe for CH activation, that can generate an aryl palladium species, and then see above, migratory insertion, rotation, beta hydride. This is one of the earliest examples. I think if you dig into literature, you'll find this is the earliest example of something we would now consider a Heck type alkene addition. And my own personal opinion is that Fujiwara doesn't deserve enough credit for many things, but particularly this early work in connection to Heck type addition. Okay, now let's consider an example from Heck himself. Now, looks similar, but a little bit different here. We have a diorganomercury species. A palladium-2 catalyst. Now note that we're under catalytic conditions. The previous example was stoichiometric. We have copper as additive, methanol solvent. So this is vaguely similar to Heck type conditions, and you're able to get the arylated product out here. So now the key point is that one of the, specifically a phenyl group, so let me draw phenyl. The key point now is that we generate a common intermediate, but we do so by a different elementary step, namely transmetallation. And an important contribution here was that this process is now turning over catalytically with copper as the oxidant. And I think these are, if I'm not mistaken, aerobic conditions to turn over the copper subsequently. So if we think about the period in history when this work was happening, note that this is the late 1960s. So the researchers were aware of the contributions from Wacker Chemie, this new this nucleopalladation mechanism, and they were asking the question: what other carbon nucleophiles might one be able to? What other types of nucleophiles, and in the carbogenic space, what types of coupled partners here might one be able to engage? So Fujiwara is asking if you can engage arenes as potential reaction partners. Heck here is asking if you can do aryl organometallic nucleophiles, and there's an interesting. Well, if you're into organometallic history, you might find this interesting. This bottom example from Heck, we would now refer to this type of reactivity paradigm where we have an aryl organometallic nucleophile and a terminal oxidant as an oxidative Heck type reaction. But then, of course, the timing here actually precedes the development of what now we call the Mizuroki Heck reaction. So how can you have an oxidative version before you have the parent version? Well, that I'm not the one who comes up with these names, but this is called an oxidative Heck type reaction. And then what we'll see shortly is the classical polarity Heck reaction. So in terms of my own preferred nomenclature, I like to talk about this reactivity paradigm of aryl palladium additions to alkenes as Heck type alkene additions. This specific reaction is an oxidative Heck reaction, and the next example we'll see as a Mizuroki Heck type reaction. So oxidative Heck with the key point that you have a terminal oxidant here and an organometallic nucleophile. Okay. I think what really propelled this field to new heights was the recognition that you could generate aryl palladium species by yet another way, and that is by oxidative addition of low valent palladium, specifically palladium-0, into now a carbon electrophile, an aryl halide. And so in papers published in close succession by Mizuroki and then Heck, this mode of reactivity was laid out. So first, and one of the points to highlight that is perhaps a little confusing at the outset, but we've talked about this before in class, is that in both cases, we'll see we're coming in with palladium-2 pre-catalysts, but these are believed to be reduced in situ to the active form, palladium-0. In the Mizuroki case, they corroborate this hypothesis by showing that palladium black, aka metallic palladium, is also competent precatalyst. So now we're coming into this same process via oxidative addition to generate a palladium-2 aryl species. And then if you think about turning this over, which we'll see in a moment, now you'll see that the overall process is redox neutral. So you don't need a terminal oxidant to turn. And it's a little bit tragic, maybe more than a little bit. It's tragic looking back in retrospect because Mizuroki made this pioneering contribution to organopalladium chemistry. Unfortunately died at a young age before he was able to see the fruits of his labor and see how some of these early concepts from his group ultimately laid the groundwork for modern catalytic cross-coupling reactions. So some people will just call this Heck-type arylation. Again, my preferred nomenclature is Mizuroki Heck-type arylation, acknowledging both key contributors. Okay, let's now look at the catalytic cycle for this Mizuroki Heck reaction. Some of it we already have mapped out based on previous discussion. So we'll just walk through in a little bit more granular detail, again, just so that everyone can see. There's some implicit step where the palladium-2 precatalyst is reduced. And so in the case of this first example by Heck, that is happening by the triethylamine base serving as the reductant. So it's donating its electrons, it's getting reduced to the corresponding the triethylamine is getting oxidized to the corresponding cationic aminium species and giving up its electrons to palladium-2 to drop down to palladium-0. That can then oxidatively add to the aryl iodide species. So help us think through here. Christine, what is the stereochemistry of this oxidative addition going to be? Are the aryl and X groups going to be what, trans to one another, cis to one another? What do you think?
Would be cis.
Initially, they will be cis to one another. Perfect. And then I have this equilibrium drawn. So what might happen next here?
Isomerize.
Cis to trans isomerization. Perfect. Now the alkene needs to coordinate. And something needs to get kicked off of the metal. So what do you prefer to kick off here? One of the L-type ligands, say a phosphine, or the X-type ligand? I don't have that specified, but in the previous examples, we saw that was an iodide. Which do you prefer? The iodide, okay. Why do you prefer the iodide? Well, let's draw that out. Let's see what that looks like. Now, one of the consequences of that is that now your intermediate will be cationic, right? You've traded a X-type ligand for an L-type ligand. So I set you up for success here, Christine, because you can answer either and you will be right. You can either displace the phosphine type ligand, the L type ligand, and you would be correct, or the X type ligand, and you would be correct. And those are two different branches, the cationic or the neutral pathway. I'm going to just delete this to draw the neutral pathway out because that's, and then we'll talk about the differences. But either is fine. We'll talk about how you choose which path to go down. So let's displace the L-type ligand here. Again, this could be phosphine, could be solvent. And now we feed directly into the steps we saw before. Migratory insertion, we need to have a bond rotation. Beta hydride elimination, dissociation of the palladium hydride, quenching the hydride with base that provides strong thermodynamic driving force because you're making an HFX base adduct that in some cases is insoluble, so will crash out of solution and turning over the catalytic cycle. So I mentioned there's two branches to this stream, either the neutral pathway as drawn. Let me specify that. There's also a cationic pathway. And so you might run this thought experiment in your mind of what factors are going to favor whether I'm going through the neutral pathway or the cationic pathway. And I think we have a handout to summarize this that I would draw your attention to. But intuitively, based on what we learned in class, I think this hopefully will make sense. So cationic pathway is favored when the X-type anion is weakly coordinating. So think here things like triflate, nosylate. I said nosylate, I meant nonylate. And think here ligands that are less likely to dissociate. So for example, bidentate ligands, where there's a significant entropic cost for dissociating one of the two arms. And there's a means by which you can read out which pathway you're in, neutral or cationic, and that's at looking at the regioselectivity with a select collection of coupling partners, somewhat analogous to what we looked at in the Spencer U test in terms of metal hydride additions. So the neutral pathway and the cationic pathway will both reliably add aryl groups to the terminal position of acrylates and related acceptors. We see regiodivergence when it comes to neutral olefins. So the neutral pathway favors alkene addition terminal compared to internal. And we see erosion of that level of selectivity when we're in cationic. But I think the big change is that when we go to enol ethers or enamides, we see a substantial switch in selectivity for the cationic pathway favoring the aryl addition to the internal position. Again, I think this makes sense if you just think about the intrinsic ground state polarization of these alkene coupling partners. More information on that in the handout if you're curious. Any questions? Yes.
Yeah, ask about the ligands switching process.
Yeah.
Is it inner sphere or outer sphere?
Well, I guess the question you're maybe truthfully asking is if it's associative or dissociative. It's a 16 electron D8 square planar, so in principle, it's capable of undergoing associative ligand exchange. I think it might be X anion dependent here because the triflate you might expect to already be outer sphere. Right? So yeah, it's a good question, Wenji. I don't think it's critical because you'll end up getting to the same products, whichever you draw. And I think we've talked about mechanistically how you could diagnose which is operative. So my understanding is that it's dependent on on the factors you'd expect it to be dependent on, ligand, X group, probably nucleophilicity of incoming olefin. But I can double check on that. Okay, let's look at one example in, this might take a little bit of time, but I think it would be worth it just so you can see something a little more interesting rather than just making still beans. So let's take an example from Varesh-Rawal's group. There's quite a bit going on here. It's an intramolecular Mizuroki-Heck reaction. And the authors expected that they would get the product shown in the gray box, and in reality got something different. And so what is going on here? There's potentially quite a bit going on. So let's go ahead and get started together. So what's the first step here? Oh, what did I do? Okay, now I can't undo that copy paste. Bear with me here as I try to do as much of this as I can without. How did I do? Let's see. I'm missing some atoms. I'll figure it out shortly. Okay, so let's just get started here. Pranali, what's the first step going to be?
Oxidative addition.
Beautiful. Okay, what next?
To get
So far, no surprises, so we'll just do what? Migratory insertion, beautiful. I'll draw this with a really awkward looking bond angle, but hopefully forgive me. So that's, those two groups are cis, and here the facial selectivity is dictated by the overall topology of the molecule. And aha, look, we've got a nice coordinating lone pair here that can form a dative interaction. And so if you had to provide an explanation, Pranali, of why this beta hydrogen elimination might not happen, then what do you think from this suggestive way that I have it drawn?
because of palladium's interaction with the lone pair.
Perfect. Chelation stabilization. Now it's rigidified, and it's similar to actually some concepts that from like my own group's research that we covered. Okay, so now what can happen instead? Well, it's just sitting there, and you see one curious feature in the product that's identified is that the olefin geometry is inverted. So how might that happen? I'll pose this to the class. Any ideas? Well, you have an organopalladium species. Let's see.
Another migratory insertion.
Aha. Alex has got it. You have an organopalladium and you have an alkene. So that we always say is a recipe for migratory insertion. What would you generate then as the product there?
You would generate a cyclopropane with the metallic palladium.
Beautiful.
Some terminal position.
Now you're going to see some very horrendous looking drawings. So you said we're gonna need to make a cyclopropane. Right. 1, 2, 3. Is this what you had in mind, Alex?
Yeah, and then I guess beta carbon elimination give us, oh no, that's not gonna work.
Oh, no, don't go with your instinct there. I think you're onto something.
Beta carbon elimination gives the basically desired product after reforming the double bond.
Beautiful. So let's look at let's draw what I mean by that. Carbon elimination. So here's palladium and here's the carbon. Which carbon do you want to beta eliminate?
Rightmost of the cyclopropane.
The rightmost. Is that right?
Or no?
I'm missing a bond. I knew, oh. I have to do that. So this one should be to what? This?
Flip over to the
Is that the right beta carbon?
Yes.
Alpha. We need a different one.
I want to break the bond between that and the suspended ring below it.
Yeah. So that's so in analogy to beta H elimination, we need a carbon that's bonded to the beta carbon. That makes sense. Good. So this might seem a little bit exotic, but actually this is a fair thematically. I'll zoom out. The key point to take away is when you're migrating, bless you, alkenyl palladium species into alkenes, it's actually quite common for them to re-react to make a cyclopropane atom. And that can be a means by which your alkene stereochemistry is eroded potentially, or it can actually turn on some new reactivity. So in like Scott Snyder's, some of his chemistry, including his quat carbon guided retrosynthetic analysis paper, they're able to engage the cyclopropane with an oxygen-based nucleophile to turn on chemistry that wouldn't be possible if there wasn't a cyclopropane.
So that beta carb eliminates to give a new like carbopalladium.
It will read. It will.
Beta hydrogen.
Correct. Thanks. Let me. Good. Any questions? Went through that quickly, but that's there's an original reference if you have any questions about it. Okay. Let's jump over to allylic substitution. Here, it will be a palladium-centric discussion, but hopefully you will appreciate that the general concepts that we'll cover also apply to other metals. So what's different about owl metal species compared to some of the other organometallic type adducts that we have covered so far in class? I think as long as we're in a high oxidation state regime, so let's say palladium 2, I think a defining feature is that the organic adduct has significant partial positive charge buildup such that it can engage in CC or C heteroatom bond formation in an outer sphere. So in some ways it is similar concepts to what we cover in alkene activation, But as you'll see, we generate al metal species by different mechanisms than we do than we generate olefin type complexes. So al metal species are susceptible to nucleophilic attack at the two termini. Also, we've seen that we've discussed that it can attack in internal position as well, but I think most of the examples you'll see in the ensuing discussion with palladium, with iridium, will be terminal attack. And this process, if you push electrons, you'll see what happens here is we're essentially attacking this electrophilic carbon, pushing electrons on to regenerate an alkene, and also reducing the oxidation state of the metal. And so this can be thought of as a reductive elimination. In some cases, it is truly a inner sphere type reductive elimination. We'll talk about this mechanistic dichotomy. And so I mentioned that the reactivity of al metal species is a little bit distinct compared to other organometallic species. So let's compare them to some others that we covered in class, such as alkyl metals or aryl metals. And the key point I want to make here is that the al metal species, and also we've encountered acyl metal species in class, and these share this feature, is that they have a low-lying LUMO that is carbon-centered, and that's their secret for being able to engage in bond formation in an outer sphere fashion. And that stands in contrast to alkyl metal species, aryl metal species, alkyl metal species, which have they do not have a low-lying LUMO on the carbogenic group, and in fact actually have nucleophilic character more often than not. Now, alkyl is maybe an intermediate case because in our own work, we've shown that sometimes alkyl fragments can act as electrophiles in reductive elimination. But first pass approximation, then you can think of these other species are polarized in a way that the organic fragment is nucleophilic, and that's not the case here. Now, within the al metal series, a consequence of this point I made about where the LUMO lies, I think this naturally falls out. But then if you think about how these will react as electrophiles, the more electron withdrawn the overall complex is, the fewer electrons it has, the more electrophilic it's going to be, and the faster it will react with nucleophiles. So a consequence of the frontier molecular orbital picture of these species is that as you go cationic, neutral, anionic, you go in that direction of decreasing reactivity. Hapticity also plays a role. We'll see in detail how this manifests throughout the class. We've talked about how al metal species and also benzyl metal species have the capacity for haptotropic shifts. They can be in an eta-3 mode. That's what's drawn so far on this page. And they can also undergo a shift to toggle to an eta-1 mode. The eta-3 mode is more reactive, more electrophilic. And you'll see this haptotropic shift because it opens a coordination site. It makes the al group when it's eta-3 has a coordination number of 2. When it's eta-1 has a coordination of number of 1. So you can favor the eta-1 mode by having ancillary ligands that can trap the vacant coordination site. And then the two different hapticities, eta-3 versus eta-1, lead to different products, linear on the left, branched. And these are in equilibrium under reaction conditions. Okay, let's take a look now at problem of the day number 1, which I have restated here. So this is going to It's really like a warm-up problem of the day, just to get ourselves oriented. We're going to treat this molybdenum CP Al complex with a nucleophile, generic nucleophile here. And then based on concepts we covered from class last time, such as the Davies, Green, Mingos rules and what we have covered so far, let's predict what the product of this will be. So just take 10 seconds to think about it, 15 seconds to think about it, and then we'll discuss. So first, which organic fragment is going to get attacked? And then if there are multiple possible products, then which will you favor? Okay, so Madison says Al terminus. So why do you prefer the Al to carbonyl or to CP?
Like we just talked about, it's more species.
Okay, it's molybdenum. It's in the, what is the oxidation state here? Plus 2. We have a linear NO, so we'd call this, and it's cationic, so we'd say this is electrophilic metal. The Al is acyclic, so if we apply those selection rules, then we should conclude that the Al is what's going to be attacked. Now, Madison, you have 2, maybe you didn't know what you're signing up for here, but you have 2 possibilities. Which of the 2 Al carbon atoms would you prefer attacking? These are inequivalent. If you think about these 2 positions, they have different spatial relationship with respect to the NO versus CO. We'll throw this open to the class. Anyone want to offer a guess? You've got a 50% chance of being right.
Attack the one, the upper one.
You would attack the upper one. Why?
Well, you could consider it trans to the NO. The other you could consider trans to the CO. So by that logic, if CO is a better trans effector, the lower position is more electron rich. But if I'm wrong, say everything the opposite, and it's still
Okay. Let's go with the say everything the opposite. I think your logic was sound. So first we need to make a comparison about NO versus CO, linear NO versus CO, which has a stronger trans effect. You concluded that CO has a stronger trans effect. This is actually subtle. If you're looking back to your trans effect notes, you'll see we don't have linear NO, but you can read about it in great detail if you want in these 2 review articles. Linear NO has varying trans effect, trans influence, depending on the properties of the metal, the other ligands are there. But let's say it's very, very small trans effect in this case. CO has a large trans effect. What do we know about trans effect? It destabilizes bonds trans to that ligand. That's the ground state effect, and then increases the rate of substitution. So if we apply that, superimpose that logic now to Allylic substitution, we would say the site with the ligand, if there's 2 inequivalent ligands, one with a stronger trans effect is going to facilitate attack trans with respect to that. And that's a rule that we'll define here. Why is that? It's in most cases likely a combination of the ground state effect and the transition state effect. In the ground state, it leads to bond lengthening, bond weakening, and that increases the LUMO coefficient on that carbon atom. More positive charge accumulation. So we apply these two rules. The first one was the one that Madison helped us define here, that we apply the Davies-Green-Mingos rules, attack the open eta3, and then we need to think about which of the two ligands has a stronger trans influence and predict based on that which site will be attacked. We'll see more examples of this trans effect, trans influence. This is confusing. Okay, let's talk now about, we're still in a stoichiometric regime here. Let's talk about synthesis of palladium pi-al species, again, with the understanding that this can be applied to other metals as well. So this is problem of the day number 2. There's actually this, if you read this paper, it's interesting. There's a lot going on here, but we're just taking a snippet out of it for the synthesis. This, I think, will potentially be, I have a little hint noted there. I don't know if anyone saw that. So let's go through this quickly. We'll first predict what the product of this reaction is going to be, and then we will try to predict what the relative rates will be across this series. So what do you think, Elin? It's going to form a pi-al, okay?
Well, the palladium will first coordinate on the off and the effect and the kicks out the estrogen people.
Okay, beautiful. So let's unpack that. You said it's going to coordinate to the olefin. It's going to kick out the benzoate leaving group. Now, let me ask you about stereochemistry. Would you expect it to form a pi-al on the same face as the phenyl or the opposite face? And why? Opposite face, okay? Why? Stereo, okay? So we've got a So we're going to coordinate this palladium 0 to the opposite face. It turns out that oxidative addition to generate pi-al species happens with inversion of stereochemistry. And so it will coordinate to the face opposite to the leaving group and also opposite to the steric bulk in this case. And out of that, we will get the pi-al here. We'll draw this down. Good. Did anybody get anything different than that? Okay, now given that that's the product, Elin, how do you expect the order of reactivity across this series to be, from methoxy to methyl to fluoro to nitro?
Actual scoring from least to the most.
Beautiful. The more electron poor the benzoate is, the better leaving group that should be, and the faster this oxidative addition should go. And I think if I remember right in this paper, actually the methoxy case even is so slow that there's essentially no reaction under the reaction conditions that they test. So what are the key takeaways here from this example? One is that oxidative addition is happening in an invertive manner. 2, that the better the leaving group, the faster the oxidative addition rate happens. That I think should not come as a huge surprise based on the oxidative addition lecture. So this is a special subtype of oxidative addition, but the same rules generally are followed. Yes.
Sorry, I might have missed it, but is the oxidative addition occurring invertively because of it's an SN2 type mechanism going into the sigma star of the leaving group, or is it just purely steric or something between?
It is it's a good question. So the invertive nature of oxidative addition to generate pi-als is is independent of this phenyl substitution. So that's a stereoelectronic feature of the mechanism of oxidative addition. And so you can in this case think of the phenyl group rather than being, maybe I didn't explain this as best as I could. The phenyl group here is not so much a blocking group, but it's a readout. It allows you to read out which of the two faces the palladium is on. If that wasn't there, then you wouldn't know if it's invertive or retentive, right? Okay, so let's talk about other ways that we can generate high Al species. I have a few drawn here, depending on how creative folks want to get. This is open-ended, so there's let's just take suggestions. We talked about already one of the most common, which is the allylic, sorry, the Al leaving group plus low valent metal, and this can be actually of two flavors here. So you can also have the leaving group at this position, and which you use can depend on synthetic accessibility, but they do have different reactivity profiles depending on the metal, depending on the ligand, et cetera. So what are some other ways? This is the palladium 0 plus allylic electrophile route. What are other possibilities? No wrong answers here. What do you think, Madison? Allene, okay, beautiful. We just talked about that. So allene plus what? Sure, let's say palladium hydride or palladium aryl. Okay, what else? I think we also, because we just talked about this, by the same token, dienes can work in this way. What else are we thinking? Chenghua, what do you think?
Transmetallate with like magnesium.
Beautiful. So now we're going to use Al nucleophile. You said magnesium, but the same could be true. Boron, silicon. Pick tin, pick your favorite. And now we're going to have palladium 2 instead of palladium 0 because transmetallation is redox neutral. What else?
CH activation.
Aha, I like it. What mechanism do you have in mind for that?
It's CMD.
Okay, so you said CMD, so let's draw that. Oh, acetate. Beautiful. And then if you want to get even more exotic, you could think about, by the same synthetic logic, some type of H additive abstraction plus palladium 1. And on the surface, that might seem a little bit ambitious, but actually this is a thread from the modern literature to generate allylic radicals this way. So Frank Glorious has looked at this in radical additions to 1,3-dienes to generate allylic radicals. And there is a high profile paper published just a few months ago now from Vlad Gevorgian's group that I'll put up here as a reference, just to try to give you a flavor for what's going on in the modern literature. So allylic substitution is both classical type reaction, but still is a lot going on in the modern literature. So I'll give you a reference there, and we'll include this in the reading in case anyone wants to read more about that. So in this case, they generate an aryl radical. Aryl radical extracts the weak allylic CH bond. That now Al radical can combine with palladium 1 to generate or at least that's the proposed mechanism. So lots of possibilities here that then intercept this common intermediate. Let's see how one of these plays out. This is the example that Madison mentioned, addition to allene. So here's an example from not too long ago. Well, I guess I'm getting old. This is from a decade ago already, but to me, it just seems like yesterday. We have Allene intramolecularly tethered to the aryl iodide. So we come in with palladium 0. That oxidatively adds to make a new palladium aryl species. The allene can coordinate as a additional ligand here intramolecularly. Hopefully everyone's seen this. And upon migratory insertion, what do we generate but a new palladium allyl species? There are no really strong nucleophiles in solution. All we have here as the additive is silver fluoride. And so fluoride, even though it is a relatively reluctant nucleophile, as nucleophiles go, it's the only show in town. The silver here plays a dual role. We've talked about silver effects. So if we don't scavenge the iodide, we might expect the iodide to come back in here, but we have silver salt, so we can precipitate silver iodide. Now all we have around is fluoride that can engage the pi allyl species, regenerates the palladium 0 catalyst, and makes the fluorinated indole product. So what are the takeaways from this example? It's that you can generate pi allyls from things other than classical leaving groups, such as allenes, and that in the past 10 years, a broader range of nucleophiles than had previously been appreciated can now be used in allylic additions. And we'll see how this manifests as well in problem of the day number 4. Okay, so now let's talk about catalysis. So far, our focus has just been on generating allyl species, and then that example from Doyle's group will be a segue into how to turn these over catalytically. So in terms of this synthetic planning, I think anybody who's in a total synthesis group and studied previous total syntheses will appreciate the role that catalytic allylic substitutions play in complex molecule synthesis. So they're able to serve as the equivalent of an SN2 or SN2 prime reaction. And the key point is that those corresponding non-catalyzed reactions, an SN2 prime of an allyl alcohol derivative, those do not work well in the absence of catalysis. So if you were to think, okay, I'm going to forego all metal catalysis, I'm going to take this alcohol and convert it to an altosylate and just do fire and brimstone chemistry, then good luck to you. That's going to be a difficult road to hoe. So this allows you for selectivity control in these valuable bond forming reactions. The nucleophiles that are most commonly used in classical catalytic allylic substitutions, and we'll talk about some exceptions to this, but classically these are what are called soft nucleophiles. So what do we mean when we say soft? We mean nitrogen-based nucleophiles. We mean stabilized carbon nucleophiles. So think here malanates and cousins of malanates, things that are in the pKa range below 25, and most oxygen-based nucleophiles. There are some exceptions. For example, I think carboxylates show borderline behavior where they can behave. They can attack competitively as inner sphere or outer sphere. So all of these soft nucleophiles that we're covering, what do they share in common? Is that they're going to attack the pi allyl in an outer sphere fashion. How's that going to manifest in terms of stereochemistry? We saw that oxidative addition happens with inversion of stereochemistry in stereoinvertive way. And because this is an outer sphere process, these soft nucleophiles are going to also attack with inversion. So the overall stereochemical effect is going to be double inversion, aka retention. Here's the general mechanism. Initial coordination of the low valent metal to the alkene, as Elin taught us, and then expulsion of the leaving group to generate the eta-3 pi allyl, which of course has the ability to toggle through haptotropic shift into eta-1 form. Nucleophilic attack then forges the new carbon-carbon or carbon heteroatom bond, generates an alkene-bound metal product bound form of the metal catalyst that then undergoes dissociation to regenerate the parent form of the catalyst. Similar to things we've seen previously. Okay, let's now take a look at some of the early history here. And we'll do this in, to parallel the coverage of the Fokker and Heck type early history. So here too, in allylic substitution, an early player was a familiar name, Jiro Tsuji. Remember that example from Tsuji's group where he took the COD palladium-2 complex and added deprotonated form of dimethylmalonate? Here, he's asking the question of what other types of organopalladiums might undergo this same type of CC bond formation with that family of deprotonated malonate nucleophiles. And he takes al palladium chloride dimer, same nucleophile. Now in DMSO and ethanol, he's able to see evidence of CC bond formation. The first prelude to allylic substitution now with stoichiometric palladium. We see we're not turning this over catalytically. We're palladium-2 at the outset, or palladium-0 at the end. Also happening during the 60s. So remember, with organopalladium chemistry, organopalladium catalysis coming online, people are asking what types of nucleophiles can we throw in here to trigger bond formation? What types of electrophiles? We've seen alkenes react. Can al leaving groups react, etc. And then several years later, important contributions from the lab of Barry Trost, I think really highlighted the potential of allylic substitution as a potentially preparatively useful tool in synthesis. So even though subsequent work from Tsuji's lab after this TL paper in 1965 had shown that this process could indeed be turned over catalytically, it still had not been picked up by the synthetic community to a great extent. And Trost changed that. One of his key discoveries was introducing triphenylphosphine as a ligand. We've seen the importance of phosphine-based ligands in the context of hydrogenation, going all the way back to Wilkinson's work, and hydroformylation. Here, phosphines are playing a leading role as well in allylic substitution. And the key point is addition of phosphine allows for much higher yields, cleaner reaction profiles. And now, because you have a ligand, you have a handle to be able to tune product selectivity. An interesting sidebar on this example from the Trost lab is that if the way that this actually was allylic starting material, palladium starting material was made was actually from the strategy that Alex proposed to us, a CH activation. An early example of this type of allylic CH activation used towards synthesis. So sometimes we think that the pre-functionalized form of a reaction came first and the CH activation form came second, but you see in the early Fujiwara case, that's not true. In this early example from Trost, that's not true. So with Trost's discovery of triphenylphosphine and its important role in promoting this type of reaction, giving higher yields, better turnover, et cetera, then of course the race was on to design chiral ligands for an antioinduction. Recognizing here that in many cases you're forming new CC stereo centers. And this is, if you think about what's going on here, this is a very challenging problem in stereo induction. Because remember, the nucleophile is approaching in an outer sphere fashion. So think about the pi owl. So you're, let's say, this pen is like the pi owl, the incoming nucleophile is coming from Wenji, and this interspace is metal. The ligand's like holding on here on the exact opposite side of where the nucleophile is coming in. So you need really well-tailored ligands to either be able to project stereochemical information all the way through the pi-al to where the incoming nucleophile is, or to twist its conformation in a way where there's only one possible incoming trajectory. And so some early work focused on p-chiral phosphines, but this didn't really get the job done. It was really only in the early 90s with the development of this ligand that we now call a Trost ligand, did asymmetric versions of Allylic substitution, the so-called AAA reaction come online, the version of Allylic substitution that we're familiar with today. And as you can see, just from the design of this ligand, this is probably not the first thing that they tried, right? A lot of iteration and mechanistic insight to get to this final form of the Trost ligand. And there's a nice chem review here. It's a little bit dated now, but I think it has a really nice insight into the genesis of this ligand design from the Trost lab. Okay, you'll see if you read Allylic substitution, catalytic Allylic substitution papers, you'll see all sorts of electrophiles that folks used. So how do you know which to use and how do you tune the electrophile if your chemistry is not working? Here's a general trend. Of course, there are a lot more electrophiles than just these, but here's the 3 commonly used ones, the general trend. So allylic acetates here are the worst in terms of their oxidative addition rate, followed by phosphonates. And one common class that you'll see are these carbonates. And so what is special about these? Why would you expect this to be a particularly attractive type of electrophile here? What do you think?
Leaving group, you lose CO2 and methanol.
Aha, okay. You lose CO2. So let's just draw the product of this. Do you lose methanol?
Oxide, which is the base.
Beautiful. But here we have an all-in-one coupling partner. You have strong driving force because of this CO2 extrusion step, and it nicely generates the base that you need to deprotonate your nucleophile. So that's the key design feature behind why you'll see these carbonates used again and again in allylic substitution reactions. Uh-oh, my Apple Pencil's running low. Okay, so this is always the most difficult thing to manage.
I've heard tell of a difference between methyl versus T-butyl.
Right. What would you expect the difference to be?
Well, I know that the T-butyl worked better in Anthony's case.
Okay.
I never really understood fully why.
Well, what would maybe one complicating factor of methoxide generation as a byproduct?
The methoxide added back to the aloe, but the terbutyl was bulky enough to basically not do that.
Exactly. So methoxide is not the most gentle thing to have around in solution. And so it can re-engage the pi-al. This is what Anthony was talking about. So if that's you, yeah, thanks for this. Insider insight. If you switch this to a T-butyl carbonate, then your byproduct here is a base that's going to be similarly effective in deprotonating your nucleophile, but now it's going to be non-nucleophilic, so it's going to have that benefit. And that can manifest not only in terms of the readdition to the pi-al, but also just any other functional groups that you might have that might be not incompatible with methoxide floating around in solution, such as if you have an ester that's prone to attack, or a stereocenter that might be epimerized. Okay, let's consider now this example. So we've talked about the trends in terms of how different substitutions on the electrophile affect oxidative addition rates. But one of the things that you may appreciate is that in many cases, the pi owl species that you are generating, if it is an internal pi owl, there may be two potential inequivalent sites that it could attack. And this will obviously, the nucleophile attack will obviously be influenced by the steric, the substitution of the pi owl, and the electronics of the pi owl. But how? That might not intrinsically be obvious. So let's consider this specific case study. And if you're interested in learning more about this and the nitty-gritty details, I direct you to the handout from today's class. But here's a case where we tried, it's designed to have a similar steric property. So we're going to generate a pi owl that's internal, aryl groups on each side, and we're going to vary the electronic properties of the aryl group. So let's consider this extreme case, nitromethoxy. Which of the two potential products do we think might be favored? Jalen, what do you think?
A few minutes.
Okay. So walk us through your thinking here, Jalen, while you're pondering.
So you have a Allylic palladium species with a acetate on the palladium. So it can be viewed as a equilibrium of both say palladium bonds.
Okay.
And one of the reductive elimination is favored and it's more stable. So
Okay, so that's what you're thinking. So which, do you have any, a guess is okay. This might not be obvious. It wasn't obvious to me when I was going through this.
I would say I would say the first one is more stable, but I think it can.
Got it. Now you invoked product stability, but we would assume that probably that this is not all in equilibrium. So maybe you mean, I guess maybe you're thinking the transition state is more stable for the product that also happens to be more stable. The product's more stable because it has a more extended conjugated pi system. So I think there are two mnemonics here that might be helpful to you. So I'll give them both to you, and if you find them helpful, then you can integrate them into your thinking. If they're not helpful, then you can come up with your own mnemonic. So one mnemonic is to think about the metal allyl as an allyl electrophile, and then think which resonance form is going to be the most stable with positive charge at which of the two positions. And oh, do I have this? Let me see. Oh yeah, okay. And in this particular case, we'd say the form that is more stable is where the positive charge is next to the electron with donating group that can take an electron density to stabilize it. And that is where the highest LUMO coefficient is going to be. Positive charge is going to build up on that position, largest LUMO coefficient, that's where the investment time. Another way is to just think about in the transition state, how do electrons flow? And they flow, what is the overall dipole of the transition state? They're flowing from the nucleophile into the pi system. So the dipole of the transition state looks like I have it drawn. And then which of those dipolar forms is going to be more stable, with the electron density flowing towards the most electron withdrawing group or towards the most electron withdrawing. So those two mnemonics you could apply to think through predicting these types of Allylic substitutions. And in the handout, there's a lot of detailed information about NMR shifts of the corresponding intermediates, and I think that can be a good exercise for you to do thought experiments about how you might expect within this series proton NMR shift, carbon NMR shift to change, and then how that would manifest in terms of product selectivity. Questions on that? So we've talked about effects of the electrophiles, and we talked about some success stories in terms of chiral ligands, but let's drill down a little bit more into some of the ligand design effects that are present within common classes of ligands. So one common class of ligands that you will see in Allylic substitutions, we saw that the Trost case, that's an example where you have C2 symmetry, but you'll see a lot of ligands in Allylic substitution that are not C2 symmetric, they're C1 symmetric. And the two donor atoms have very different properties. So step back and think why that might be the case. It goes directly back to this idea that we mentioned that Alex helped us walk through of the trans effect / trans influence. When you have two coordinating sites with very different trans effects, then that's going to dictate which of the two alkenyl carbon atoms is selectively attacked. So let's look at the case of FOX, which is a commonly used ligand in Allylic substitutions. We have one phosphine coordinating site, one nitrogen coordinating, sp2 nitrogen coordinating site. Which has the higher trans effect / trans influence? Phosphine. So that is going to direct substitution to the carbon trans to it. And it just so happens that in this case, all of our chiral information sits directly at that site. So that's the underlying ligand design principles between these unsymmetric ligands. One of the positions is directing the key bond forming event to happen proximal to the site where the stereochemical information is. And you'll see many ligands. Again, in the handout, there's a whole list of ligands, but this is an important design principle that is recurring here. We'll see one more example of this in just a moment. Okay, let's talk about nucleophiles. We've talked about this regime on the right, which are the classical nucleophiles, the so-called soft nucleophiles. And so we can take, we'll compare and contrast the results of this classical soft nucleophile diethylmalonate deprotonated form of sodium salt in this Allylic substitution with stoichiometric, but stereochemically defined palladium high-owl, and then contrast that with the case of a canonical hard nucleophile, aka a Grignard reagent. So something that's going to undergo a different pathway, react via transmetallation. So what we've already seen, we'll just restate what we've already seen, is that this is going to react classical soft nucleophile. It's going to react the this outer sphere pathway. Let me draw this one. Backside attack. And we see the overall outcome is invertive. Now, how's that going to change when we go to a Grignard reagent? Now the difference is that we will first have a quick transmetallation. Remember, Grignard reagents are known to transmetallate quite quickly. Now we have another ligand on the metal. So that's going to want to be in its 801 form. And now we will reductively eliminate to get retention with respect to the starting pi-al complex. We see some leakage of stereochemical information. I guess I don't have this drawn here, but you can assume the starting complex has higher EE than 79%. I'll fill that in for next year's notes, but we see some leakage of stereochemical information. So how does that happen? That will set the stage for something we'll discuss in a moment. So now the key contrasting point is that with hard nucleophiles, AKA substituents for which the corresponding conjugate acid has a pKa higher than 25, we typically will see in catalysis a mechanism of inversion followed by retention. So it will overall be invertive. Because this reductive elimination now is happening from the 801 form, you would imagine this to be highly sensitive to sterics and thus take place at the oh, sorry, let me back that up. So with palladium, this happens at the less substituted terminus and will typically give linear products. And that is true with both of these mechanistic paradigms, soft or hard. But you can tune this ratio by the nature of the alkyl. You can also tune this ratio by the nature of the metal catalyst that is being used. So classically, palladium gives linear substitution products in the case of these terminal pi-als. Whereas probably the one that's most commonly explored in the modern literature is iridium to give branched products. So there's ligand dependence, there's metal dependence, but first approximation, remember that for a terminal pi-al, palladium's going to go linear, iridium's going to go branched. There's a lot of important work that has been done with copper, and copper is great for mediating allylic substitutions with hard nucleophiles such as organozincs, Grignards, organolithiums. The features of this are somewhat similar, somewhat different. They're actually covered. I think they're sufficiently different that they're covered as a separate chapter of the Hartwig textbooks. In the interest of time, we won't go into those details, but I direct you to that chapter. I think the key feature of copper allylic substitution is that you have a initial alkene coordination of the copper and then a rate limiting oxidative addition to make a sigma form pi-al species. That's sort of the defining feature, and then transmetallation with these hard nucleophiles followed by reductive elimination. Because of these mechanistic features, it's overall invertive, namely stereo invertive oxidative addition, stereo retentive, transmetallation, reductive elimination. And there's a beautiful suite of robust antioselective methods developed by the likes of Alexakis, Hoveda, many other key contributors in this area. Okay, so let's talk now about, let's jump into problem of the day number 3 here. which I have restated, or recopied here. So we'll consider the case of a terminal pi owl addition of a classical soft nucleophile. It gives three products, the two that I've drawn here, as well as the branched product. So this is not a super selective process. And the question I want you to consider in this is, how do you explain generation of both the Z on the left and E substitution products based on the mechanism that we have discussed so far in class? Dylan, you're making eye contact. What do you think?
Are we gonna make the palladium pi owl?
Okay. Palladium pi owl, good. And what would you expect the stereochemistry here to be in terms of the EZ stereochemistry of the initially generated pi owl? Would you expect any change from the Z?
At this point, I would think it would be the same 9-to-1 ratio.
Okay. And then what's going to happen next?
Would we have a migratory insertion with our nucleophile?
Well, how are you going to get to the erosion here?
Oh, we need to go to 8-to-1.
Ah, okay, beautiful. And this, I guess if we do it this way, this might not get us to, is that right? This won't get us to eta. I think if we go this way, then we can rotate. Is that what you're thinking, Dylan?
Sorry, what was that?
We're saying go 8-to-1, and then that will allow you to have a bond rotation that you need, so that when you establish 8-to-3, now you've flipped the stereochemistry. One, two, three. And now you have two pathways that can get you to the two corresponding products. And the key is this 8-to-3 to 8-to-1 to 8-to-3, or sometimes called pi to sigma to pi. Isomerization mechanism. Questions on that?
What is like the driving force for that to go from 8-to-3 to 8-to-1?
Well, in this case, it would probably be that if you consider this intermediate versus this intermediate, you would probably say that the one on the left is more strained. And so in isomerizing overall Z to E, you're relieving allylic strain. And so then it will be a matter of what are the relative rates of that 8-to-3, 8-to-1, 8-to-3 isomerization versus the relative rates of which the two intermediates are trapped. It will determine the overall product ratio. So I'll stop here, being respectful to the